Okay, hope you can hear me. I'll get started. Wanted to start with brief announcement, reminder that test one is coming up on next Tuesday. It'll be in this regular class time, and it will be a Canvas test. And I'll have you log in or connect to Zoom so that you can ask any questions through the chat during the test. The test format will have multiple choice questions on it, sort of patterned on the lecture quizzes. It'll have numerical answer questions on it, kind of patterned on the homework problems, and it'll have a long problem that you'll fully work out and submit your solution, kind of patterned on the recitation problems. I'll post towards the end of this week a practice Canvas test, so you'll get a better feeling for the format of the test. There is online old tests of mine and the formula sheet, so you might want to take a look at those too, but of course they're not they were not a Canvas test. Any questions on all that? Let me get the chat up here. Okay, well, if not, I'll move on with the lecture class, and if you do have questions, you can ask me at the end of the lecture class. I'll stay on a little while at the end of the lecture class. Okay, so last class we introduced the effects of forces on the motion of bodies, and specifically we introduced Newton's three laws that describe the influence or effects of forces on the motion of bodies. Today's class, I'm gonna begin with just a quick review, one slide review of Newton's three laws. I'm gonna describe briefly sort of the cast of today's classes. There are three forces. They're the gravitational force, the normal force, and the tension force. So I'll say a few words about each of those, gravity, normal, and tension forces. And then we'll get on to the bulk of the class, the real content of the class, which is to work through some illustrations or work through some examples of applying the laws of motion to different situations. And there's going to be two classes of situations that we're going to look at. One class is what we call equilibrium, and the other class is what we call non-equilibrium. And so, you know, our problems that we work through today, they're kind of the dramas or the action movies that we're making out of these casts of characters, which are gravity, normal force, and tension. Okay, so let me just summarize Newton's laws of motion, or remind you of Newton's laws of motion that we met in the last class. As I say, they're really the sort of cornerstones for today's class, or the foundations for today's class. So first law, if you remember, the first law was a statement about what happens to an object, what happens to a body when there's no net force acting on that object or acting on that body. And if there's no net force acting on that object or that body, then if that body were at rest, it would stay at rest. If that body were in motion, it would stay in motion. And so that net force being zero could be because there was simply no forces acting, or it could be that there is some balance of forces acting that add up to zero net force. So that's the first law. Second law was a statement about how things move in the presence of a force, or presence of a net force. So they describe, the second law describes how a body will accelerate if there's a net force on the body. And that acceleration will be in proportion to the force that's acting, the net force that's acting, and in an inverse proportion to the mass of the body or the inertia of the body. So the larger the force, the greater the acceleration. The smaller the force, the smaller acceleration. The bigger the inertia or mass, the smaller the acceleration. The smaller the inertia or mass, then the bigger the acceleration. So the same force on an elephant and mouse will accelerate the mouse a lot, will accelerate the elephant just a little. Also, it's important that force has a direction. It's a vector quantity. Acceleration has a direction. It's a vector quantity. So the acceleration is in the direction of the force. The acceleration is always in direction of that net force. Okay, third law of motion. Third law of motion is the statement, the fact that forces always come in pairs. Forces always come in couples. There's no single forces. If object 1 exerts a force on object 2, then object 2 exerts a force back on object 1, and we call that action and reaction. So the two bodies influence one another. If two masses interact, they both exert forces on each other. If two charges interact, they both exert forces on one another. And this equation here describes the third law, that those two forces are equal in size and opposite in direction. Anyway, that's the summary of the three laws of motion that describe quantitatively how forces influence movement. So now I want to introduce three forces that we're going to work with in today's class. And we're going to expand on this number of forces in the next class. But today's class is all about the action of these three forces. It's gravity, it's normal, and it's tension forces. And if there were no gravity, normal, and tension forces in today's class, then we'd just be floating around in space. If we were still, we would stay still. If we were moving, we would stay moving. It's the gravity, the normal, the tension forces that create the action, create the drama in today's class. So gravity. We met gravity a little at the end of last class. Let's return to it at the beginning of this class. So imagine dropping an apple. If you drop an apple towards the ground, then as it falls towards the ground, it's experiencing the gravitational force. We call that the weight. And the gravitational force is in proportion to the gravitational acceleration. It's the mass times the gravitational acceleration. And as an example, if you had a 1 kilogram apple and you dropped it towards ground, that 1 kilogram apple experiences a 9.8 Newton force, gravitational force towards the ground. It's the product of the 9.8 meters per second squared acceleration of gravity times the 1 kilogram mass of the apple. And so that's kind of the rule book for gravitational forces in today's class. And for each of the forces, we're going to introduce a little rule book. Okay, here's the next force for today's class. It's the normal force. Call it the normal force. It's an example of a contact force, meaning it occurs when two objects, here is the apple and the table, are in contact with one another. So we get a contact force. In this case, is called the normal force. So the situation we're imagining, the situation we're considering, is an apple that's at rest on a table. And that apple that's at rest on a table, it's at rest and it's staying at rest. There's no net force on that apple. There's a gravity force downwards, however, and that's pictured in this overhead here. Let me get my pen working. So here's the gravitational force, and it's pulling the apple downwards. But the table is exerting on the apple an upwards counteracting force. It's the normal force. And here's the normal force. We normally call gravity the weight of the object. So here I've used this symbol W for gravity. Here's the normal symbol we use for the normal force. It's this uppercase N here for normal force. And in this situation of the apple on the table, the downwards pull of gravity is being precisely balanced by the upwards push of the normal force, the contact with the table. And as a result, you get zero net force, and the apple is at rest and is staying at rest. So for example, if it was a one kilogram apple, there'd be a 9.8 newtons strong downwards gravitational pull on the apple. And there would be a upwards 9.8 newton strong normal force on the apple. And it would be those two 9.8 newton forces, one up, one down, that would add together to make the zero net force on the apple. If you want to imagine or picture, visualize where that normal force arises, how it comes about, it's actually because, you know, the apple's made of atoms and molecules, and the table's made of atoms and molecules. And when the apple is at rest on the table, the atoms and molecules of the apple and the atoms and molecules of the table are being squished together. And because they're being squished together, they push back. And that push back is the normal force. So it comes about actually at the atomic molecular level of the atom and the table, as the atoms and molecules of the apple and the table interact with one another. Anyway, this is the second sort of character in today's class, the normal force. Let me go on to the third one. It's the tension force. So for the tension force, we're now imagining an apple in a tree. And here is the apple in the tree. This is the stem on which the apple is hanging. Again, in this case, the apple is at rest and staying at rest. So there's no net force on the apple. But again, like the apple on the table, it's not that there's no individual forces acting on the apple. There are actually individual forces acting on the apple. And one of them is the gravitational force. So downstairs here, I've marked the gravitational force. There's pulling the apple downwards towards the center of the earth, but counteracting that force is an upwards tension force exerted by the stem of the apple on the apple itself. And I've denoted that upstairs here. So as we usually do, we call the gravitational force the weight of the apple. So I've denoted it W downstairs here. Tension force, we normally denote that uppercase T. I've denoted it upstairs here. And those two forces are equal in size, opposite in direction. And so the resulting net force is zero. And if the apple's at rest, it will stay at rest. So as an example, again, imagine that apple was a 1 kilogram apple, then there's a downwards gravitational force on that apple. It's 9.8 newtons downwards. There'll be an upwards tension force on that apple, 9.8 newtons upwards. And the addition of those two oppositely directed forces, 9.8 newtons down, 9.8 newtons up, gives us the net zero force on the apple. And so it's at rest, it's going to stay at rest. Again, if you want to visualize or imagine or picture where that force arises from, that tension force, it arises from the atoms and molecules of the stem and the atoms and molecules of the apple. Those atoms and molecules in the stem and the apple, they're being pulled apart by the gravitational force. And when they're pulled apart, they pull back. And that pull back is the tension force that's supporting the apple against the downward pull of gravity. And so this is our third character in today's class. Okay, so let's now move on to the examples part of today's class, the illustrations part of today's class. And as I mentioned at the beginning, is going to be two distinct parts to this. One part is going to be examples of forces in situations we call equilibrium. And then the second part will be examples of forces in situations we call non-equilibrium. And this picture here is an example of equilibrium. So the stones in this picture are at rest and remaining at rest, and that's what we call equilibrium. Now, it's not that there's no forces acting on those stones. There are forces acting on those stones. But the net force that's acting on each of those stones in that pile of stones is zero. And that's what we mean by equilibrium. And so that's what we're going to study first. And then later on, we'll look at a couple of examples where it's non-equilibrium. Imagine this arrangement of stones collapsing and falling to the ground. That would be non-equilibrium. Things were at rest and things started to move. And that's non-equilibrium. Okay, so this is going to be our first example of a situation involving the equilibrium of forces. And the key thing about the equilibrium of forces, as I mentioned, is that if you add up all the forces acting on an object and it's in equilibrium, then the sum of those forces adds up to zero. It's not that there's no individual forces. There are individual forces, but the sum of the forces adds up to zero. And that's the situation we have here in this problem. So in this problem, we've got a 2-kilogram box, we're told. Here it is. We're told it's at rest on a frictionless incline at an angle of 20 degrees. And so here's a little picture. Here's the box, and here's the incline. So here's the 2-kilogram blocks. Here's the 20-degree incline. And this box is supported by a combination of the normal force that's acting on the box and a tension force that's acting on the box. And so there's a string here, and there's tension in the string that's helping support the box. And then there's this contact with this surface incline here, and that's helping support the box. And so there's a combination of those two forces, the normal force that we just introduced, the tension force that we just introduced, that are conspiring together to support the box and keep the box that is at rest, keep it staying at rest. So it's an interesting and sort of intricate example of equilibrium, because we got gravity pulling the box down, we got tension pulling the box up, we got normal force pulling the box up, and somehow they conspire to make no net force, zero net force on the box. And we're going to explore this situation. And specifically, we're going to calculate the normal force for the box, and we're going to calculate the tension force on the box. Okay, so if I wanted to compute or calculate the tension forces and the normal forces on the box, I would definitely start with a diagram. And diagrams become really important, really useful, really helpful when you're thinking about forces, both forces in equilibrium and forces in non-equilibrium. So I'm really starting with a diagram here. In the diagram, so you see the incline in brown, you see the box in blue. I've marked the the mass of the box. That's something we're told, 2 kilograms. I marked the angle of the incline is something we're told. Those are kind of the parameters of the problem, the numbers that define the problem for us. And then I started adding to the sketch of the box on the incline, the forces that are acting on the box on the incline. And so what we're going to focus on first is this red downwards force, this blue mostly upwards force, this green mostly horizontal force. And so these are the three forces that are acting on the box, and I've drawn them as if they were acting on the center of the box, which is a way that we can think about their action. We'll come back to this later, but for the moment, let's just think about them acting on the center of the box. So the red force is the gravitational force. So it's the weight of the box, and it's straight vertically downwards, and its strength is the mass, 2 kilograms, times the acceleration of gravity, 9.8 meters per second squared. That's 19.6 newtons. So we know everything about this force. We know its direction downwards. We know its strength, 19.6 newtons. And this arrow, the red arrow, is to indicate both those things. It's directed downwards, that's the direction of the arrow. Its length is 19.6 newtons, that's the size of the force. Then I've added the two other forces that are acting on the blocks here. So the first one I've added is the normal force, and that's this blue arrow here. Now the thing about the normal force is, it's why we call it the normal force rather than just a contact force, is it acts normal to a surface. This force that helps support an object on a surface, helps support the apple on the table, is at right angles to the surface. So the key thing about this sketch when I drew the normal force is that there's a right angle between the direction of the force and the plane of the incline. So there's 90 degrees here. Anyway, I pictured the normal force. Now I know its direction, it's normal to the surface, but right now I don't know the strength of this force. So that's something we're going to have to figure out. Third force I pictured is the tension force. That's over here on the right-hand side. Tension force, the rule for its direction is that the tension in the string, tension in the stem of the apple, it acts along the string or along the stem. So I've drawn the normal force acting in the direction of this string here that's supplying the tension force. So kind of like the normal force, I know its direction, but I don't know the size of that force. And that's also something we want to figure out. And so this picture here is basically a picture of the situation. And picture of the forces, the three forces, W, N, and T, gravity, normal, and tension. And then I've done one more thing on this picture. And this is going to be very useful as we do the calculation. The extra thing I've done on this picture is resolve forces, resolve each of the three forces really, into their components or their parts or their contributions that are along the axis of the incline, so parallel to the incline in my sketch, and perpendicular to the incline, 90 degrees to the incline. That's what I've done over here. I've called the direction up the incline, I called it the X direction. I called the direction perpendicular to the incline, I called that the Y direction. And the way we solve this problem mathematically is to resolve these forces into these components, so along the incline and perpendicular to the incline. Well, for the tension force, that's easy because it all acts in the positive X direction. For the normal force, it's easy. It all acts in the positive Y direction. For the weight, it's a little more complicated though. If you look at the weight, it has a component that's along the Y direction, in the negative Y direction. And for the weight, it has a component that's in along the x direction, the negative x direction. And so this weight of 19.6 newtons, we're going to resolve into two pieces. One piece that's perpendicular to the incline and one piece that's parallel to the incline. And this piece that's perpendicular to the incline, I'm going to call it WY because it's along the y-axis. And you can figure that from the weight times the cosine of the angle of the incline. And you can figure the piece that's parallel to the incline, this piece here. Again, you can figure that from the weight times the sine of the angle of the incline. And that's this little calculation here. So WX and WY are my two components of the weight that together make the full weight that act along the incline and perpendicular to the incline. W sine theta and W cosine theta are the opposite and adjacent sides of a triangle made out of the weight as the hypotenuse, and W sine theta, W cosine theta as the opposite and the adjacent. And that triangle is indicated here. And this angle here, theta, is the same as this angle of the incline theta. If you want to imagine why that would be, imagine reducing the angle of the incline, making the angle of the incline almost horizontal. Then this angle here would also reduce, become almost 0 degrees. And so this angle in this corner of this triangle and this angle in this corner of this triangle, the same angles. Okay, so that's going to be an important part of our calculation to do that resolving of the forces into their horizontal and vertical components. The other important part of our calculation is, or the key to the calculation is the application of the equilibrium condition. So equilibrium says that the sum of the forces acting on the box is 0. So that means in this case, the sum of the weight plus the normal force plus the tension force, those three vectors added together must add up to 0. And so we're going to work with that idea to solve this problem. Okay, so now I've got a little lecture quiz. Let me post that for you. And it's about this problem. And let me at least show it to you first. It's about it's sort of really using your intuition to compare the sizes of these forces, the normal force and the tension force. And without any calculation, I'm going to ask you to think about which one you think is bigger. Is tension bigger? Is normal force bigger? Or are they the same size? Those possibilities. And so you should see a quiz posted now. Okay, so the answer is that the normal force is bigger than the tension force. Let me tell you how I think about it without doing any calculation. Supposing we made the incline angle, that 20 degrees, supposing we made that extremely small angle, maybe 1 degree or maybe less, so we'd lower the incline. Then you can probably imagine what's supporting the block. Really, it would just look like the block on the table. If we make this angle almost 0 degrees, it's just like a block sitting on a table. It's supported by the normal force, as we discussed earlier, and there's no need for the strain. What about if we did the opposite? Supposing we make the angle, the 20 degrees, supposing we make it very large, nearly 90 degrees. In that case, right, there's no support that's offered by the incline. It's just like a cliff face. We're supporting the block by the string. So the two extremes of this problem, where the block sits on a horizontal surface and where the block hangs next to a vertical surface, are the two situations that we talked about when we were introducing the forces. This situation would be the apple on the table, and then it's the normal force that counteracts gravity. This situation over here would be the apple on the stem of the tree, where the tension force would support the apple. Now, we're much closer with 20 degrees here to horizontal than we are to 90 degrees. There's 70 degrees here. And so the normal force is larger here, and the tension force is smaller here. If it had been 20 degrees to the vertical, then the tension force would be larger and the normal force would be smaller. So that's how I think about that one. And that sort of intuition is helpful when you're solving problems, because you can, when you come up with a number at the end, after working through the math, you can readily check whether it makes sense or doesn't make sense. Okay, let's move on with the calculation. And here's my calculation. It's just on one slide. Oh, and it's now gone away. Here we are. Okay, so upstairs here is just the picture that I made on the prior slide showing all the forces. Sorry. Try again. It's just the picture showing all the forces and including the different components of the weight. And over here, writing out the equilibrium condition, that the three forces must add up to zero if the thing's at rest and staying at rest. So then what I did was rewrite this equilibrium condition, that the sum of the three forces is zero, but write it out in terms of the components of the force that are along the incline. So that was the x direction, the components of the force that are perpendicular to the incline. That's the y direction. So not only is the sum of the three force vectors zero, but if you were to add up the components along the incline, that must be zero. Otherwise, there'd be movement up and down the incline. And if you add up the forces perpendicular to the incline, that must be zero too. Otherwise, the box would jump off the incline or crash through the incline. So equilibrium applies to the components as well as the force vectors themselves, the x and y components in this problem. So for the x components along the incline here, there's two of them. There's tension, and there's this portion of the weight, W sine theta. And importantly, tension is in the positive x direction, up the incline. That component of weight is down the incline in the negative x direction. And so that's the sum of the forces that are acting along the incline, and those must add up to zero. And so that's equilibrium in the x direction. Similar thing for equilibrium in the y direction. So in the y direction, there's the normal force that's acting perpendicularly to the incline in the upwards, in the positive y direction. And then there's this component of gravity, W cosine theta, that's acting down the incline. And so those are the two forces that are acting in the y direction. And again, there's one of them that acts in the positive y direction, that's the normal force, and one of them acts in the negative y direction, that's a portion of gravity, and that's how they conspire to cancel each other out. So this is equilibrium in the y direction. So having written that down, we can use those two equations then to solve for the forces, solve for the unknown tension force and unknown weight. And so that's what I'm doing down here. So I can take equation number one And I can rearrange that equation for the unknown tension. That's what I've done on the top line here. Let me get my pen back. From equation number 1, I rearrange to get an equation that the tension, unknown tension, is the weight times the sine of the angle of incline. And from equation number 2, I rearrange equation number 2 to get an equation for the normal, which is equal to the weight times the cosine of the angle of the incline. And so then at that point, you know, over here on the right-hand side, I know the weight. And I know the angle of the incline. So I can fill in the weight of a little under 20 newtons, the sine or the cosine of the angle of incline, and I get these solutions for the normal force and for the tension force. And we see indeed, so the tension force is about 7 newtons, the normal force is about 18 newtons. The normal force is indeed bigger because the incline angle was small. The tension force is indeed smaller because the incline angle was small. And so that's how we analyze the situation. So it's quite an interesting problem if you think about it really. You've got that innocent little box sitting on the incline. It's at rest and staying at rest. But beneath that at rest and staying at rest is really this subtle cancellation of 3 forces kind of working together, or at least tension and normal force working together to counteract the gravitational force. And by taking on these very precise values, tension 6.7 newtons, normal force 18.4 newtons, they perfectly cancel out the downwards 19.6 Newton force of gravity. And that's the equilibrium that's going on here. Okay, so let's push on if I can. And let's look at a second problem. And I'm going to show you a little example of this situation. But let me explain it in a few words first. So we're imagining that we're supporting a traffic light here. We're going to support this traffic light. And the mass of the traffic light is 0.2 kilograms. And we're going to support it by this arrangement of cables. So it's hanging from this cable number 3, I'll call it, that's vertical. And then that cable that's vertical is attached to 2 other cables. This one on the left, I'll call it cable number 1. This one on the right, call it cable number 2. And what we're actually going to think about and what we're actually going to figure out is the tensions in these 3 cables. We're going to calculate these 3 tensions. So we're going to calculate tension in this cable 3 that's in the vertical direction. And then we're going to calculate the tensions. I'll draw the tension arrows here, or the force arrows here, in cable number 1 on the left and cable number 2 on the right. Specifically, what we're going to imagine, actually, rather than focus on the traffic light, we'll focus on this little point here, this knot, where the cables are all connected. That's at rest and staying at rest. That's in equilibrium. And so there must be a balance between these 3 forces acting on this knot, acting on this point. And so that's the equilibrium that we're going to consider. Let me just show you a little, it's not going to be an exciting movie, but it's a movie of this situation. So I'm going to stop sharing that guy. And I'm going to share another screen with you. And so here it is. This is, I'm back in chemistry, physics, large lecture room here. And I've set up with significant help. I was incapable of doing it myself. I've set up this demonstration of the traffic light situation. So what you're seeing here, here's the traffic light where my mouse is. And it's actually a 200-gram traffic light. That's the mass down here. There's a little short cable here, number 3. And then there's the cable on the left, number 1, we called it. Cable on the right, number 2, we called it. And at this moment, you see that the angles of the cables are both 45 degrees to the horizontal. So this cable is at 40, on the left is at 45 degrees. This one on the right is at 45 degrees to the horizontal. So this is not actually the situation that we've got in the problem. And then we're going to change this arrangement and turn it into the situation we have in the problem, where we got one angle of 37 degrees and one angle of 53 degrees. Now, the other interesting thing you want to keep an eye out, it's a little hard to see in this movie, but this device up here on the left, this device up here on the right measures the tension in the cables. So it actually measures that tension force in the cables. And there's a red arrow here that indicates the strength of the force. Now you can't read this, but it's a little over 1 Newton. This guy's a little over 1 Newton. And we're going to see what happens when we change the angles, whether those tensions also change or whether they don't change. Let's watch that. So this angle here is 45 degrees and there's a little over 1 Newton tension, and that one is also 45 degrees and it's a little over 1 Newton. And that's with the 200 gram mass hanging on the cables. So then I came along and I rearranged it. You can see the angle on the right is now a bit bigger. The one on the left is a bit smaller. So it's 37 degrees on the left and 53 degrees on the right. We still got the 200 kilogram mass here, but you'll notice that the force with the larger angle has now got a bit bigger. The force with the smaller angle has now got a bit smaller. So the forces did change when I rearranged the angles from both being 45 degrees where the two forces were the same to now with 37 and 53 degrees where the forces are different. So here I went and changed it the other way around. Now I put 53 degrees over on the left and 37 degrees on the right. And if you look at it there, the interesting thing is that as I swapped the angles, still with the same 200 gram traffic light hanging, now the force on the left is bigger with the larger angle on the left. The force on the right is smaller with the smaller angle on the right. And so this is the situation we're going to investigate. This is what we're going to study. So let me get rid of that. We'll stop sharing it. I'll get rid of it. It's going in my video collection. And let me share my slides again. And so this is the situation we're thinking about. Look, we got 37 degrees, the smaller angle over here on the left, 53 degrees, the larger angle over here on the right. And we've already seen in the demonstration that the larger angle has the larger tension. We measured that. The smaller angle, the smaller tension. And so let's try and figure that out. That's what we're going to do now. Okay, so again, I always start these problems with a nice diagram, a nice sketch of the forces that are acting. So I can really visualize, picture, imagine the equilibrium that's going on. In this case, as I mentioned, I've got to get my annotation back. In this case, the way we're going to work is we're going to consider this sort of vertex of the tensional force on the left, right, and the tension force in the vertical string. And we're going to think about that equilibrium. That point is at rest and staying at rest. And it can only be at rest and staying at rest if the sum of these three forces add up to zero. Now, there's an important point here. Okay, there's one tension vertically downwards in string 3. There's one over towards the left in the blue string, one over towards the right in the green string. We actually know the tension in this string that's immediately above the traffic light, because that string is supporting the traffic light. It must be counteracting the weight of the traffic light. The weight of the traffic light is the mass of the traffic light times the acceleration of gravity. That comes out to be 1.96 newtons. So that tension force T3 we call it, is 1.96 newtons. So this guy we know. We're told it basically because we're told the mass of the traffic light, and it's vertically, and the traffic light is hanging vertically from that string. It's just like the apple hanging from the stem. The apple is just hanging from that stem vertically. Then that 1 kilogram apple experiencing that 9.8 Newton force of gravity, there must be a counteracting tension of 9.8 newtons in the stem. And that's exactly the same situation here. So really our only task here is to find the unknown T1 and the unknown T2. Find what those two forces are. And so again, I went about the same sort of procedure as I did for the block on the incline. I'm going to resolve these forces into two components. And the useful components here are horizontal and vertical. So I call the horizontal direction towards the right, I call that positive X direction. The vertical direction upwards, I call that the positive Y direction. And I'm going to resolve these three tensions into those components. Now, the tension T3 is just vertically downwards, so that one's easy. But T1, as you see here, because of this 37-degree angle, it has a component horizontal, I call it T1X, and a component that's vertical. And similarly for T2, right, the one that's going towards the right, because of the 53 degrees here, it has both a horizontal component that I call T2X and a vertical component that I call T2Y. And so when we do the calculation, we're going to resolve the equilibrium, resolve these tensions into these components. That's the method we're going to apply. But perhaps the key thing to start with down here is the equilibrium, that the sum of these forces acting on this point must add up to zero. So that's equilibrium. And in this case, it's T1 plus T2 plus T3. Those three vectors added together must equal zero. And so that's the equilibrium condition. And then we're going to apply that. Okay, so let's do the calculation now. So clear that. Go on to the next slide. First step is, in doing this calculation, I'm going to write this equilibrium not as the vector T1 plus the vector T2 plus the vector T3 is zero, but in terms of these X and Y components. So let's start by doing that. And I've done that downstairs here. So if you look downstairs, the top line is the sum of the X components of the forces must be zero. That's equilibrium in the X direction. The bottom line here as the sum of the Y components, that must also be zero. And so if we resolve the equilibrium into those components, let's do that. Well, in the horizontal direction, there's just two components of the forces. There's this guy here, that's in the negative direction. And there's this guy here in the positive direction. And so that's what I filled in. There's a horizontal force to the left, negative direction, that's T1X. There's a horizontal force to the right, that's the positive direction, that's T2X. And those are going to add up and cancel each other out. And then here I just wrote them in terms of the angles and the magnitudes of the tensions. So T1x is next to the 37 degrees. It's the adjacent. T2x is next to the 53 degrees. It's the adjacent. And so T1x is T1 times the cosine of 37 degrees. And T2x is the T2, the magnitude of the tension, times the cosine of 53 degrees. And so I just expanded these components in terms of the unknown tensions, that's the T1 and the T2, and the known angles. I did the same thing downstairs here for the force in the y direction. So for the force in the y direction, I'm adding up all the components of forces in the y direction. So in this case, I've got a upwards component, T1y. I got a upwards component, T2y. And then I've got a downwards component, which is the entire force, T3. And so I've written that down here. And again, I filled in the sine 37 degrees and the sine 53 degrees to pick out of, T1y and T2y are not the entire forces T1, T2, not the entire tensions T1, T2. They're components of those forces T1 and T2. And so I put in the sine 37 degrees, sine 53 degrees to pull out those components. Remembering, look, the T1y and the T2y are opposite the angle. So it's sine theta that picks them out. Okay. I'm hearing somebody else's conversation now, so I've got to somehow mute that. Okay, so now let me go ahead and do the calculation, if I can. And the calculation amounts to taking those two equations and solving them for the two unknowns in those equations. So I've written out here in this overhead, I've written out those two equations again, but I did one extra little thing that'll keep the equations looking a little simpler here. Remember we had the cosine and the sine of 37 degrees and 53 degrees. Well, I filled in the numbers for those cosines and sines of those two angles, the 37 and the 53 degrees. And so that's where these four numbers came from. Those are in the top equation, the cosines of the two angles, and in the bottom equation, the sines of the two angles. So that's where they came from. And then if you remember, in the case of the y direction, the y components of T1 and T2 cancel each other out. In the case of the horizontal direction, the vertical direction, the vertical components of T1 and T2, they actually work against gravity. They cancel gravity's downwards pull. And so that's the reason these two equations look a little different. Okay, so now we've got to solve those for the two unknowns. So let me do that. So the first thing I did here was I solved for tension T1. And the way I did that, and there's lots of ways you can do this. So my ways, there's nothing special about my way or better about my way. There's plenty of ways that you can solve the two equations for two unknowns. I took this equation number 1, rearranged it for T2. So if you rearrange it for T2, it says that T2 is 1.33 times T1. So immediately we know that T2 is larger. And T2 had the larger angle, T1 had the smaller angle. So our expectation from the experiment was that it was larger, and it is indeed larger. But anyway, I took this rearranging of equation number 1 and used that to replace the T2 in equation number 2. So what I'm going to do is replace this guy here, and that's what I did downstairs here, with 1.33 T1. Because then this becomes an equation with one unknown, T1 over here. And so I can solve it for that one unknown. And that's what I get here. I find that T1 is 1.18 newtons. And so that was my solution for T1. Then it's easy to go back to the two equations and find the remaining force, the T2. Actually, we already know, right, that T2 is 1.33 times T1. So all I've got to do is take that equation and fill in the now known T1 force. So take this equation, plug in this answer for T1, and multiply by 1.33, and I get 1.57 newtons. And so that's the solution for the second force. And that's exactly what we saw in the overhead. In the overhead, we saw, not in the overhead, in my magical movie. In my magical movie, we saw that the tension in the cable with a larger angle, the 53 degrees, was bigger. It looked like it was about 1.5 newtons, and it is 1.57 newtons. And the tension in the cable that was making the smaller angle, that was smaller. It would look like it was a little over 1 newton, and it is a little over 1 newton. We found it's 1.18 newtons. And so we've been able to solve this problem quantitatively by applying the equilibrium condition. Again, just like in the block on the incline, for these three tensions, there's this delicate balance that's going on that keeps the block or the knot, if it were at rest, to stay at rest. Those three tension forces in this problem, or the weight, the normal, and the tension force in the prior problem, all add up to make zero net force. That's that sort of beautiful equilibrium that's going on. Okay, let me clear this. And I want to look at, in the last 15 minutes, one example of a non-equilibrium. And then we'll continue the story of non-equilibrium in the next class. Okay, so here's an example of non-equilibrium, this collapsing building, right? In this case, there are net forces acting on the building. And because there are net forces acting on the building that at some point was at rest is no longer at rest. It's falling towards the ground. It's accelerating towards the ground under the influence of the various forces that are acting on it that are not now in equilibrium. So this is the big distinction between the pile of rocks in the equilibrium situation where they were at rest and staying at rest, and this building in this situation where it's in non-equilibrium and it was at rest, but it's going to be no longer at rest as it collapses. So that's what non-equilibrium is. And we're going to look at this example of non-equilibrium. So in this problem, we're told that a 12 kilogram shopping cart. Here it is. Slides down a 5-degree incline. Slides down the incline without friction, and the incline's length is 8 meters, and then it hits this parked car. And we got to figure out the speed at the moment of the collision. So the key things in this problem are, we know this is 12 kilograms, the shopping cart. We know the angle of the incline is 5 degrees. And we know the distance the shopping cart travels down the incline. That's 8 meters. And we've got to figure out over here, what speed does it hit my BMW? So that's our challenge. And this is a situation involving non-equilibrium, just like the falling building, right? The shopping cart was at rest and it starts moving and it keeps changing its motion, and that's non-equilibrium. And to solve this problem, we're going to use not the first law of motion, Newton's first law of motion, which applies to the equilibrium condition, but the second law, Newton's second law of motion, which applies to the case when it's non-equilibrium, when things are accelerating, because things are accelerating here. I got a little video of this to show you first. Not with a BMW, but let me do that, and then we'll solve the problem. It won't take long to solve the problem. Okay, I'm forgetting to share it. I've got to share it. Where are we? Okay, here I am, and behind me is an incline, and in my hand is a block, and we're just going to slide the block down the incline as an example of non-equilibrium and of second law of motion. And I've slowed it down a little because the block tends to slide pretty quickly, and we'll see it clearer if we do it more slowly. So the block starts at rest, and once I release it, there's a situation of non-equilibrium. The forces aren't balancing, and then it accelerates down the incline. Now I just lowered the incline. Again, I released it. It started from rest. It accelerated down the incline. But you might have noticed one thing. When the incline was steeper, its acceleration was larger. When the incline was shallower, its acceleration was smaller. When the incline was steeper, there was a different balance of the forces that created a larger net force down the incline. When the incline was shallower, again, there's different balance of forces that created a smaller force, net force, down the incline. So the interplay of the forces acting here, which are the gravitational force and the normal force, was different and depended on the angle of the incline. And of course, you know, right? If you let a shopping cart roll down a shallow ramp compared to a shopping cart rolling down a steep ramp, it's going to go faster. It's going to accelerate more down the steep ramp. It's going to accelerate less down the shallow ramp, go slower down the shallow ramp. And it's because of the different balance between the normal force and the gravitational force in those two situations. And we're going to explore that. So let me unshare this one. And let me share my slide. Here we are. And let me go on to the solution to this problem. And I think I do it in just this slide and the next slide. So we've got we got plenty of time here. The first thing, of course, I do, and every problem, I'm going to draw a diagram. Every problem involving forces, for sure, I'm going to draw a diagram because they just help you imagine, visualize, picture, and understand what's going on. And so that's what I'm doing here in this drawing. So I got to get my pen working again. So in blue here, here's the block, here's the cart on the incline. Here's the incline itself. And I've marked or written down the parameters of this particular problem. So the mass of the shopping cart is a parameter. The angle of the incline is a parameter. And also I didn't mark it here, but being at rest initially was a parameter in the problem. And then I started sketching the forces that are acting on the incline. So in this case, in this frictionless incline, there's just two forces. There's gravity that's acting vertically downwards. That's the rule for gravity. And then there's the normal force. And that's acting normal, right angles, 90 degrees to the surface, to the incline. And so for gravity, in red here, or the weight, we call it, well, we know the mass, so we know the force, the weight, is 12 kilograms times 9.8 meters per second squared. So just under 120 newtons. So we know both for gravity, we know both the size of the force and the direction of the force. For the normal force, on the other hand, we know the direction of the normal force is perpendicular to the incline, but we don't know the size of the normal force. Now, we could go ahead and calculate the size of the normal force, but that's not actually so important to solve the question that we were asked, because we were asked about how fast the cart is going when it hits the BMW. So actually, I'm not going to, in this problem, figure out the normal force. I'm really, in some sense, not going to worry about what the weight was. What I want to know is the net force that acts down the incline. And that net force is due to the combination of the normal force and the weight force. And it's that net force that creates the acceleration of the object down the incline. And it's that net force that will determine the speed of the object at the end of the incline. So we're really going to be interested in that. So I show these forces because you can see the non-equilibrium. This blue arrow and this red arrow can't add up to zero. And we're going to figure out the net force. And so I just stress that fact here. Look, the car isn't in equilibrium. These forces don't add up to zero. They patently can't add up to zero because there's only two of them and they're not in opposite directions. They must add up and produce a non-zero net force, which is going to drive the acceleration of the cart down the incline and determine the speed at the bottom of the incline. So my first step was actually to solve for the net force and the acceleration of the cart down the incline by thinking about the equilibrium and by thinking about the equilibrium in these two directions. So thinking about non-equilibrium. Having said all that about non-equilibrium and then called it equilibrium, which was stupid. I'm sorry about that. It's non-equilibrium here. I'm going to think about the non-equilibrium in the for the cart along the incline. Now, actually, in the direction perpendicular to the incline, this y direction here, there is an equilibrium. the normal force is being balanced by this component of gravity, W cosine theta. So these are equal and opposite. But this is the interesting component, the horizontal one. That's where the action takes place. In that direction, the sum of the forces is not zero. It's the net force, which by Newton's second law is mass times acceleration. So this is how we're going to find the acceleration. All I got to do is fill in the sum of the forces in the x direction. And the sum of the forces in the x direction, well, look, normal's not in the x direction. Gravity has a portion in the x direction. There's a portion of it that's perpendicular x direction, so that doesn't count. What we want is this is the force, the only force component that's acting in the x direction. So the sum of the forces in the x direction is W sine theta, and that must equal mass times acceleration by Newton's second law. And so that is going to determine the acceleration because we know the weight, we know the mass, we know the angle of the incline. Everything else other than the acceleration we know. And so let's solve that. And that's what I've done down here. I've rearranged that equation. I filled in that the weight is mg. And then when I rearrange that equation, oops, sorry. Can I get back? Here we are. So I rearranged this equation here for the acceleration. When I rearranged it, I plugged in the weight being mg. I canceled out the m's in the numerator and denominator, and I get this simple expression for the acceleration. It's just the acceleration times the sine of the angle of the incline. It's fantastically simple. And that's really how Galileo, if you remember, diluted gravity using this sine of the angle of the incline. So you don't see the whole gravitational acceleration. You see a fraction of the gravitational acceleration. And in this case, with an angle of 5 degrees, it's a small fraction. 9.8 times the sine of 5 degrees is just an acceleration of 0.85 meters per second squared. So a very small fraction of the gravitational acceleration. Last slide coming up. Sorry. Once you know the acceleration, it's then easy to figure out the velocity at the bottom of the incline. That's a bit of kinematics. And so here's the picture of the kinematics. On this picture of the kinematics, oops, sorry, keep doing this. On this picture of the kinematics, I filled in the things I know and the things I don't. So, for example, I know I'm going to travel 8 meters down the incline with an acceleration of 0.85 meters per second squared. I know the initial velocity was 0. I want to find out the final velocity. That leads me to this equation here for the speed at the bottom of the incline. And if I rearrange this equation, this piece cancels out because we're at rest to start with. I get this simple equation for the velocity in terms of the acceleration and the distance traveled. I fill in the numbers, and this is the speed that the cart hits the BMW at.